This presentation is the theory to understand beams. Beams are elements that transfer vertical loads horizontally. When you have a beam, the load will be transferred to columns or to the base of the building. And usually there is a combination of bending and shear. Those are the elements that we'll be studying today. We will understand what is checking a beam. We will speak about tributary areas, loads, and look some examples where shear force diagrams and beam moment diagrams are analyzed in the beams. Engineers need to check the beams, need to look if the beam that we want to design will support the loads. And what we try to test are three elements. First, the stability. There is here the definition of stability, but in few words, what we want is that the beam will not fall over, that will be stable, will not be moving. We speak about a condition of equilibrium or steady motion, but our beams are not elements that move, are elements that are supposed to stay in a place where we will forget about this steady motion and we'll take that our condition of equilibrium is that the beam do not move. It's not an object that is flying in the sky, moving at the same speed, and therefore we can consider that it's in a steady motion. Motion is not, it's a stable element. Well, stability means will not fall over. Second, strength. Strength is that the beam will not break. And finally, functionality. This is very important. We can have an element that will not fail, will not break, but maybe deflect a lot. And if it is deflecting a lot, even if it is strong to support the weights, people may be afraid to use that element. Well, imagine a bridge that is completely deflect. That is not convenient because it's not functional. It doesn't need to deflect too much. If you're in a building that is moving too much, even if it's resisting the weight, that will be a building that is not functional. Well, what we want to do when we check a beam, we want to know the shape and the dimensions of the element. In order to do that, we need to have the span. We need to have the loads, and the loads will allow us to understand where are the reactions. And finally, the material, the shape, the dimensions, and if the beam will be able to support the specific strength and deflection that we want. But before doing all these calculations that we'll be working with them instructors too, first we want to understand what happens when we have a load in the beam. And what will happen is that the beam will have some kind of deformation and will suffer shear and will suffer some moment or bending. What and how that happens? The beam will have some loads, and the beam, similar to the columns, will pick up the load halfway of its neighbors. Imagine that we have a structure like this one, and the structure is divided in 9 parts. Well, there are 9 columns, and we will have a line that divide, like you can look here, the space between the column, and each one of the columns will be supporting a specific area. In this particular case, all the columns are supporting the same weight because the columns are in the center of the tributary area. But if I move the column in one side, for example, I move the column of the corners in the corner, the columns that are in the middle will be supporting more weight. The same happens here in the right side. Those vertical elements are beam, and we have beam A and beam B. The separation between beam A and beam B will be moved, let me go back, will be divided into parts. And we can look that the beam A is supporting all the area that is green because there is nothing to support in the left side of beam A, but the beam B, the vertical beam B, is supporting half the distance between the beam A and beam C, that is the next one. That means it's supporting all the way, halfway to its neighbors. Well, tributary area is very important because for every beam and for every column, we need to understand what that element is supporting. In all that area, in the tributary area, we will have dead loads. And what we will do, as I explained before, are code values per cubic foot or square meter. We will multiply by the volume and area supported. Imagine that in that area, we have only, that is our case here, we only have this load of this transparent area. Or imagine that here we have the load of the green area for beam A. We will look how thick is that green material, how tall and how wide is, and we multiply by the weight that this particular material, that can be concrete, for example, has. And we arrive to the conclusion, for example, that this surface is 5 square feet, and multiplied by the particular thickness, we will have, for example, 6 cubic foot. And well, what we need to do is to just multiply that number by the weight of every cubic foot that we had, and that will give us the weight of the dead load of the elements. The same will be with the live load. The live load is code value, and we will multiply by the area supported. Well, in few words, imagine that the area in green here, let me go back. The green area here have 4 square feet. Well, depending the use of the building, we will multiply by a factor. If it is residential, we'll multiply by 50. That means that the weight of the live load for the beam A is 50, and for the beam B is twice bigger, is 100. Well, in that case, we have the loads that the beam has, the beam had, and in that way, we can understand that the loads will be supported by the reactions. And we already know that, because there are 2 types of loads. One is a point load, that is the one that we look here in the left side, is just in a point, and after a distributed load. A distributed loads are like many loads, point loads together, one after the other. It's like you have books, one next to the other, and every book have a page, and every page have a weight, and if you move a little bit to the left or to the right, you have additional pages, that means additional weight. Well, what the load will do 2 things. One will create shear, and second will create bending. Bending is when the element will start to bend and create that curve. Shear is when you have a weight that will break the beam, as you can look here. Well, if we look at section of that material, we put a weight in the middle, and we will have some area of compression in the superior part and some area of tension in the inferior part. In few words, if we had, for example, we write a line here with a separation, for example, of 3 inches, as I explained you in the video of introduction of this book, of this chapter. We put a weight in the top, and this element will bend by here, and therefore something like this will happen. You will have less of 3 inches in the superior part, more than 3 inches in the area that is in the bottom, and exactly 3 inches in the middle. This element here is an axis that do not change of dimension. Instead, in the superior part, we'll have compression, it will become smaller, and in the part that is in the bottom will become longer. That axis is called neutral axis, and it's an axis where there is not tension, there is not compression. But the other thing that can happen to the beam is that this force is strong enough to break the beam, like happens when you cut a paper with a scissor. Well, that will create that shear force, and the beam will be suffering of both things. In beams, it's more important the bending than the shear. That happens especially when the beam have a long span. When the beams are very short, then shear can be more important. Well, when we design the beam, the idea is that we will understand that the bending moment is very important, and this importance increases with the span. And as I told you, in short span, instead the shear is dominant. For example, when you have a pin that is connecting a part of an engine, then this connection is short, well, maybe will not bend, will just break. Beams in buildings are designed for bending, as I explained in the classes before, but are checked for shear. Well, first, we understand and make sure that the bending is working, and after we look if the shear is working. That doesn't mean that the diagram of shear needs to be made before. We made the diagram of shear before to make it the diagram of bending, but we just have the result. We're not checking. We know what is the maximum shear. After we check if that material is able to support that shear. We will not be doing this for the moment. In this class, we'll just calculate the maximum shear. Well, we need to quantify the effects. Well, first, we have a beam, and as you know, we have some forces in the superior part. In this case, only one, and we have two reactions. And the idea is that we need to find the reactions using the conditions of equilibrium. And the first condition of equilibrium is that the vertical reactions need to be equal to 0. The same happens if we have a cantilever beam. We have a force W. Well, we need a vertical force of the same value, W, in the wall that supported this cantilever beam. And this W will create a moment, will tend to bend this element. In few words, what will happen is that that beam, having that force, will tend to bend like this. It may break because of the effects of shear, but it also will tend to bend like here. And well, that is a moment that will be producing this point, because this bending will tend to move the beam down, and in order to eliminate that possibility, down, no, I mean clockwise, and in order to eliminate that, you need a reaction that moves the beam counterclockwise. Let me clear everything here. Okay. Well, how you calculate these particular forces and moments is very simple. We imagine that we got the beam, what we have been doing until now. If we want to calculate the force in this particular place, and force means the two possibilities, bending and shear, we cut the beam and we look what happens at the left, or we look what happens at the right. And that will give us some diagrams. For example, imagine that we have a beam like the one that we have here. Let me draw it again. This is a beam that has a reaction at this point. This is the reaction, have a force that is W. Well, if I need to do the diagram, what I will do, I go to the start and end of the beam and make these lines. Nothing happens in the middle because W is just a 10. And how will be the shear force? Well, if this W is 10, for example, the reaction needs to be 10 because there is only one reaction. Well, what I will be doing, I will be starting in 0. Let me change color. I will start in 0. I will go up 10 units, straight, nothing happens, and I go down. Remember, it's like doing a bank account and looking your balance. 10 going up positive, nothing happens, 10 going down. This is the shear, and that is what we have there. When we cut the beam in this point, what shear we have? 10. And we cut here is 10. Why? Because, for example, if we cut in 1, we will tell, well, we have 10 here, and that is the shear that we have in that point. If we want to look, the summatory of shears will be 0 because we will have 10 in one point and 10 in the other point. Okay? It's no matter that one area is bigger. It's matter that we have 10 only in each one of the sides. It's constant, as you can look there. Let me clean here. And for the moment will be something similar. Let me go again. We have the shear. Here we have the beam, sorry. And this beam have a reaction over there. Reaction of 10. W of 10 equal W. I just made my dot lines. And we already had before the shear diagram. Go up, nothing happens, go down. And for the other diagram, that is the moment diagram, I start in 0, I finish in 0, and what I will do is that I will tell myself, if I cut the beam just before R2, I have 0. If I cut in 1 unit, if I cut in 2 units, if I cut in 3 units, what is happening? And what is happening is that the force that we have is W. Well, we will multiply W by the distance that separate. Well, in this point, W is multiplied by all this distance. Well, it's 10 multiplied by the distance that imagine is 10, is 100. But at the end here is very small, it's almost 0. And that's why we will tell ourselves this is not something that will work. We will need to start from the left side as I show you. And doing so, we arrive to this diagram that we have over there. Let me try to draw this again. We calculate the moment here, and it's reaction multiplied by 0, disappear, but the W will be multiplied by the big distance. Let me clean this. The same will happen in this case. We have a cantilever beam. We calculate the W in the middle, and the total W will be an element that is straight. If we have a force that is distributed, we will just multiply by the distance. And we'll have this type of diagrams when the shear is not distributed in the element. I mean, an inclined one will become a curve. And there are formulas that can help us to do this when the beam is very small. Sorry, when the loads are very, very simple. And that will give us a positive shear and a negative shear. Well, let's go again. How you do the diagram? Well, you just imagine that you have here one at the start, one at the end, and you go up at the start, nothing happens, and you go W1 because you got this, nothing happens, you go W2, because no, you have this one, W, nothing happens, you go straight, you have W3, you need to go down W3, and that depends of the values, how much you will go, nothing happens, and finally you need to close in 0. Well, reaction 2 need to be equal to this distance. That is mandatory in order to make sure that the beam is closing. For the moment, it will be something similar. We will just understand how that works. Well, let's look at the shear, the shape. When you have point loads, you will have always straight lines. When you have distributed loads, you will have triangles. That is why it's simple, because here you just need to go up, and because nothing happens, you will go straight, and because you have another one that is negative, even if it is positive, you will have also the same. You will have this rectangle 1, this rectangle 2, in case that you have another positive. But in this particular case, we have that this one is positive, this number is going up, nothing happens, this number here, this load is negative and go down and close the beam. However, when you have distributed loads, you need to imagine that this is a weight and this weight change and became bigger, bigger, and bigger with the time. Well, you start in 0, you go up, whatever is the reaction, and you start going down according with the information that we got. Let me clear this and go to the next. Well, what the shear will do to a beam, the shear will tend to create like split in a wooden beam, also can create some damage in the concrete beams. It will normally, you will need to have some reinforcement in steel in order to eliminate the possibility that that piece of that particular part of the beam will break like this horizontally, but will also be able to split the beam vertically. Both things can happen. And well, that will make that the beams will have moments, and the moments can be positive or negative. Why? Because we can have forces in the string that make the beam to look like a sagging curve, and the other will make the beam to look like a smiling curve. Well, one can be positive, one we consider negative, and it's no matter what you prefer, but most books tell that the simple beams will produce positive moments when elements happens like this, when it's like sagging, and you can have positive and negative moments depending the type of loads that you had. When you have a distributed force, because the type of deformation that the beam has, we will tell that the moment will be curved. And that is something that maybe you will not understand as a theory, but I think that looking at the diagrams, you will be able to do it. The important is that when we have the bending moments, we want to know what is the maximum value. As you can look here in this example, the maximum value in the curve is the tallest number that is here. But the maximum value can be positive or negative. If this being had a different type of forces, and for example, became a being with this form, this will be the maximum number. It's no matter that it's negative. That will be the max. Well, if we have a central beam, the bending moment will be a curve like this. And it is a little bit, sorry, a rectangular line like this. And it's a little bit difficult to understand because we don't have all the other diagrams. But in few words, that is a little bit what will be happens according with the tables. Well, don't feel afraid if you don't get this information yet. Don't feel afraid if you don't learn those formulas, you don't need them. That is only to show you what normally happens in the diagrams. But you will be doing the diagrams by yourself and in a practical way, and that will allow you to understand what happens easier, and that is what we'll be doing in the next classes. This concludes the presentation.